Okay, welcome this morning to the 2011-12 run of two modules. One is called Industrial Control and one is called Control Systems Engineering. These are being co-taught this year because the content is essentially the same. And I know that some of you, I think third years are on Control Systems Engineering because it's a level 3 module, and second years are on Industrial Control, it's a level 2 module. The content is the same, the assessments are slightly different. That's how we're dealing with it. But they're being co-taught because obviously it saves them a bit of time. So, the structure of the course, we have one 1 hour lecture per week. Okay, that's this slot. And then each of you will have a 2-hour tutorial every week as well. In the first semester, those are going to be standard tutorial sessions in flat teaching rooms. In the second semester, they'll be lab-based. Like I said, 2 modules co-taught, but the assessments are different. So don't feel like, if you're a second-year student, don't feel aggrieved because you're doing a level 3 course. And the same if you're a level 3 student, don't feel aggrieved because you're doing a level 2 course. Like I said, the assessments will be different. There's 24 weeks in the year, okay? 14 of those weeks we're going to be covering control, okay? And 6 weeks of those will be sensors and actuators, transducers and things like that. It's delivered by myself. Hi, my name's Ben, for those of you that don't know me. Ben Drew, okay? Neil Larson is delivering some more. He'll be doing the later sessions of control. And then Sabir Gowri will be delivering the stuff on sensors and actuators in the second semester. So yes, like I said, there's tutorials. The first semester will be classroom examples and problems. Okay, tutorial sheets are available on Blackboard, along with the solutions. And in the second semester, there'll be some lab work that you'll be doing, which will involve Simulink, DC motor control, and looking at sensors and actuators as well. In terms of assessment for this module, if the slides will work. Assessment, finally. Okay, there's one coursework, okay, it's a lab report, and it's also group-based, so you'll be working in, I think we're saying a minimum of 3 per group. I can't remember exactly, but obviously details will be provided to you. And there'll be one report for the group, okay? And that's 40% of the module. The exam, which is after the Easter break, you have one exam in the summer, that's going to be 60% of the module. And in terms of a reading list, indicative reading list, these are the sort of the books that you can go to if you need to refer to somewhere else to get some more information, or if you're particularly interested and want to look beyond the scope of this course, then these are the suggested reading books. But in a sense, if you come to the lectures, okay, and work through the tutorial sheets, you should be fine in terms of what you need to know for the exam and for the coursework. Having said that, this is not a course you can cruise through, okay? It's quite tough. There's, in some respects, it's quite abstract, some of the stuff we talk about, okay? And there's quite a lot of maths involved too. So it's something that you so obviously come to the lectures, because that will help you in terms of the content. But it's also really good, you'll need to make use of the 2-hour tutorials, okay? Because we've only got 1 hour contact time outside of that time. And you will need the tutorial times, okay? The 2 hours. That's why we've given you 2 hours of tutorial time per week. So I'm just giving you that as a warning. It is a tough course. Like I said, things can be quite abstract, okay, in terms of concept and the content. But if you come to the lectures and you go to the tutorials and you work diligently through the tutorial sheets, making sure that you keep up with them every week, and you do the problems and stuff, and if you've got any questions, obviously the tutorial sessions are where you can ask those questions, then you should be fine, okay? But like I said, it's not one of these courses that you just come to the lectures and you'll be, that's all you need to do, okay? You are required to do a bit of work for this one, unfortunately. So the aims and objectives for Control Systems Engineering and Industrial Control, okay? Well, there's 2 broad areas. The first is control. Okay, and the first thing we look at is system modelling, because essentially control is all about controlling a system, okay, control systems engineering, it's in the title, okay, but before we can control it, we need to know how the model behaves, or how the system behaves, and to do that we can create a model, okay. So the first item that we're going to discuss primarily today is going to be system modeling, okay. The way control engineers model systems is by the use of these things called transfer. Now it should be transfer functions, not transform functions. But so that that's going to be something that we're going to cover in the next couple of weeks. We then can move once we know how the system behaves, or how the system that we're trying to control. If we understand that, we can then apply some control and look at the performance of that system. Okay. Frequency response is an alternative method of measuring the performance. Okay, there's two main domains in control. One is the time domain, so looking at the response as time increases, and the other way is looking at the response at different frequencies of input. Okay, so these are the two ways that we look at control. And then system identification is about going in the reverse direction. We're given a frequency response or a time response, and then we have to determine how the system behaves. And often, in real life situations, say you're given a system and say, I need a controller for this system. Well, first off, you've got to work out how the system behaves mathematically. And so that's going from the system identification back to modelling the system. Okay, so that's what that bit's about. Then the last bit of this control section is all talking about controller design, because there's various different methods of designing a controller that will achieve what you want to do. And this is looking at some of those alternative controllers. And then the last section, like I said, is on sensors and actuators. This is all about things like electric motors, transducers, generators, all that sort of stuff. And there'll be some lab work based around that as well. So today's lecture, we're going to talk about, we're going to introduce control as an idea, as a concept. Okay, I'm going to go through some examples. I've got a couple of examples here. I'll be showing them to you in a second. I'm going to go through the basics of control. What do we mean by control? What are the sort of fundamental building blocks that we're going to build upon throughout this course? We'll look at what does this mean, open and closed loop control? Okay, it's quite a simple concept, but it's important to understand. And then there's design steps that we go through. Okay, all the way through this semester, that'll be following these design steps. The first of which is system modelling, which is what we're going to cover today. Okay, and then we've got some examples that we'll do on the screen that are based on the tutorial sheet questions that you'll have this evening, or from now on. In terms of tutorial sheets, before I start, the tutorial sheets are on Blackboard. You have to download them yourself before the tutorial sessions. That's all. And the solutions will be posted generally the week after the week that they go up. Okay, so control. What is a control system? Well, a control system is a device, or a number of devices, that can manage or regulate or command the behaviour of a system, another system. Okay, and the system can be anything we can think of. Okay, the example that we've got here is the human body. Okay, there's a human body as a system, and we control our temperature. Once you get above a certain age, a few months, you can start to regulate your own temperature. And we do that, basically we've got these inputs, be that the ambient temperature around us, whether we're in the sun or whether we're ill, okay, that will affect our body, and our body will exhibit a body temperature, okay. And then what we can do, as we grow older, like I said, we build up actions, okay, that will help us regulate the temperature. Obviously, if we're too cold, we'll start to shiver, which will heat up our body, okay, to bring the body temperature back up. Or if we're too hot, we'll start to sweat or perspire, okay, which will cool the body down. And so this is an example of a control system, a temperature control system, okay, with the human body. Now, there are many applications for control systems. Physiology, that's the one I've just used, okay. They even use control systems in economics. But obviously we're not economists or biologists. We're going to use it in engineering, okay. And there's many, many fields of engineering where control systems are used. Hydraulics, electronics, mechanics, they're just three broad examples. But you know, almost everything we can think of will have a control system in, okay? And then obviously there's many simple examples. You're driving your car, okay, and you just get on the motorway, so you want to bring the speed up of the car up to 70 miles per hour, okay, so you apply some more pressure on the throttle pedal, okay, or the accelerator, and that will then command, in a sense, the engine and the vehicle to gain in speed, okay, and obviously that will result in actual speed. That's a control system. We have a controller, which is you and the throttle pedal, and we have what's known as the plant, which is this engine and vehicle put together. That's why there's a dotted line around it. A room fan, okay, to cool the room. Okay, there's going to be a switch on that fan. It could be multi-mode in terms of different speeds, okay. You want a desired amount of cooling. You apply the switch. The switch will control how much electrical power is going to the fan, and the fan will then turn itself on, okay, and will give you some cooling. So like I said, this is the controller, okay, these two things here, and these are what's known as the system or the plant. And it's this system or plant that we're going to try and model first off, okay. Some more examples. We need control systems that are very complex. Those two are very simple. But, you know, aircraft control systems, all the things that are controlling the ailerons and flaps and horizontal tailplane and rudder and all that sort of stuff on an aircraft are examples of control systems. The driver will give an input, the controller will control how to regulate that system, and then the system will operate, hopefully, in the way that you want it to. Anti-lock braking systems. Obviously, with a braking system, anti-lock braking systems need to know whether the wheel that you're braking has locked up, okay? And so there's a control system that will be checking to see whether that wheel system is locked up. If it has, it will then apply the anti-lock braking system. A very simple example. And many, many, many manufacturing processes will have control systems. You know, now with a lot of manufacturing now is very automated, robotic, okay? And all of those robots and automatic machines will need to have a control system so that, you know, whatever, you know, the raw materials that go in will come out as the product that you want to make. And so that manufacturing processes are heavily reliant on control systems. I've got some examples here, okay. Simple meter ruler, okay. And if I treat this as a pendulum, okay, there's two equilibrium positions. This is one of them, obviously, hanging down. Okay, the other equilibrium position is standing up, inverted, okay, an inverted pendulum. Now this is an equilibrium, okay, but it's what's known as unstable equilibrium, because if I just let go, it will fall down, yeah? Okay, but I could apply a control system using my hand, okay, and the control system, I can keep it balanced for quite a long time, okay? Just by looking at what the thing is doing, okay, and moving my hand accordingly, I can keep the thing balanced, okay? This thing here is a control system that will do this. Here again, I've got an inverted pendulum. This is free to move. And what we've designed is we've got a controller down here that in this controller, we understand what the pendulum is doing. We've done the mathematics and programmed the controller so that when I put the pendulum up, oops, let's see, let's get it going. The cart will move backwards and forwards, keeping that pendulum upright. Okay? An inverted pendulum control system. It's a bit old and hasn't been used very much. There we are. But yeah, you can see it's a control system. But to give you some other ideas of what, I've got some videos so we can go back. Let's go back to there. This is a single pendulum, okay? This one is a triple pendulum. Triple pendulums are highly chaotic, okay? Many degrees of, well, here it says 2 degrees of freedom, okay? The cart, and the triple, it was hanging down, and just from the control system, it can actually balance a triple pendulum, okay? That's nuts. Look how chaotic the movement is, okay? It'll do it again in a second. Just by understanding the dynamics behind it, they can control a system that will balance a triple pendulum. Impressive, no? Oops. Another control example of a control system. This is called a ball robot. Okay. There's a robot that can balance itself on top of a ball. There's the actuation of it. Okay, it's just moving this ball around. Okay, but we put it back on its top. So there's the robot. There's the ball. Okay, so there it's balanced on the ball, and the guy picks up the 10 kilo weight, and it balances that 10 kilo weight. And he's got a remote controller, which is what he's doing, and he can push it around or disturbance it, so it'll return back to where it was. Okay, and then another thing, he can move it around just using his finger. Okay, and the thing maintains balance. That's impressive, no? Yeah, you can see what's. This is the applications of control. He's made a wheelbarrow now, omnidirectional wheelbarrow, and he's got 3, and he can, the thing's balancing. So there's that as well. Okay. I don't know whether any of you have heard of Big Dog. Big Dog is a robot that was made. I think that it's got military applications because it can traverse all sorts of different environments. Here it's going up through a wood. Now watch this. The guy kicks it over, and the dog does the whole leg over leg to keep itself upright. And then the next clip, it's walking on ice. And watch what it does when it slips up. And this is a machine. It's not a real human thing or the dog thing. It's a machine. Okay, so there's some examples, but perhaps the most impressive example, okay, of a control system. It's much less. Let's get rid of the sound because the sound is awful. Right, there we are. This is a bird, okay? A bird. And it's stationary because the wind is blowing, obviously. And that bird is keeping itself completely stationary, okay? And it's using, obviously, its feathers and wings and various, tail plane and stuff to maintain its stationary position so that it can look on the ground and hunt, okay? It's a kestrel. But that's seriously impressive a piece of control. If you ever see that in real life, it's amazing. See what they're doing. Okay, but these are all control systems, and this is what we're learning about. To do this mathematically is extremely difficult. Okay, it puts the Big Dog and inverted pendulums into their position because this is really tough to do. Right, so there we go. So there's some examples of control systems. I hope that gives you a little bit of insight into what we're talking about. Okay, so some basics of control. What is common for all these systems? Okay, well, essentially, there's going to be some quantity, okay, that we want to maintain at a specific value, or perhaps there's a range of values that we want to be controlling, okay? There's a series of values, okay? And so there's this quantity that we need to maintain. And so there's a few things we need to do to maintain that. We need to understand what the system needs to do, okay? Obviously the specification. And we need to assess how well the system is doing it, okay? And then we need to obviously take control if something needs to change, okay? And there's 2 types of control. There's open loop, okay? Turntable example, so you've got a battery power, which has got a speed setting, okay? That goes through some form of amplifier. And that controls the motor, which then controls the turntable, which will give us the speed. All very well, okay. Well, what happens if we change the turntable to be a heavy one, or we put a mass on the turntable? Well, obviously that's going to change the relationship between the turntable and our speed setting, okay. But we have no idea of knowing that, okay. But that's what's called open loop control. And we can represent this with like a block diagram. So we've got a setting, okay, the voltage goes through an amplifier, which controls the motor, which controls the turntable to give us the speed. That's open loop control. Now closed loop control, the same example. Okay, we've got a battery, we've got an amplifier, we've got the motor that turns the turntable at a specific speed. But this time we're measuring the speed of the turntable with a tachometer, okay? That measures the rotational speed of something. And what we're doing is we're taking that signal from the tachometer, taking it up to this summing junction, okay? And we're comparing it with the setting that we desired. And then based on that setting that we desired and the measurement, we can then alter what the electrical power going to the motor to change the speed, okay? This is what's called closed loop control. And so we've got a desired speed going through an amplifier to the DC motor to the turntable, giving us an actual speed, okay? We're measuring the actual speed using a tachometer, and we're comparing that actual speed with the input, okay, to give us an error. And then based on that error, we can then speed up or slow down the turntable. And this is called closed loop control. And many, many control systems will employ this task. Excuse me, I seem to have caught freshers flu already, despite not having taught any freshers. Cruise control is another example of closed loop control system. We looked at the car accelerator issue a second ago. Well, here's cruise control in your car. You've got a desired speed, you set it on your car. That will then control the throttle, which will then control the engine and the vehicle to give you an actual speed. And say you're driving along, you've set the cruise control at 70 on the motorway goes up a slight hill, obviously the car will slow down if you don't alter the throttle position. Well, if the car slows down, you then have a difference between the actual speed and your desired speed, which is measured through the speed sensor, and then based on that, you'll get an error signal. The error signal will apply more throttle position, which will give you more power, and you'll go up the hill at the same speed as you want. And the same when you go down a hill, the car will speed up. Okay, again there'll be a difference. The error will cause the throttle to lift off a bit, and the car will slow down. Okay, very simple closed loop control system. The output is compared to the input, and the error is used to drive the system to what we want it to be. Another one is another example. Closed loop control system, generally a bit simpler. You set the temperature on your oven, okay, if you've got an electric oven, and then as you turn the oven on, you'll hear a little switch go, okay, and that will turn the power onto the heating element. Okay, and when the oven's reached the actual temperature, which is measured by a temperature sensor, it'll turn the switch off, because what you've got is it will reach a temperature just above your set temperature, okay, that sensor will measure it, and it'll compare that to the desired temperature, and if the desired temperature is lower than the actual temperature, it will turn the switch off, the heating element will turn off. The oven will cool down a bit, and then it will go back round. Once the oven reaches a lower threshold, it'll turn the switch back on and heat the oven up again. Okay. So these are all examples of closed loop control. Output is compared to the input, and the error is used to drive the system. Okay. So if we look at a generic system, okay, we have a demand signal, okay, going through this summing junction, and then we have a controller, be that a switch or whatever, to control the plant, okay, which is our system, which gives us an output. And then we take the output, we measure that using a sensor or transducer, and that gives us what we know as feedback, which we feed back into this summing junction, giving us an error, and again we just keep going around the loop until we've achieved the output position as close as possible to the demand position, okay? Simple closed loop control. So this is what's known as a block diagram. We're going to cover those in a lot more detail in the 5th lecture of this course. Okay, the plant provides the system output. The controller takes the control input and provides the control output, okay? And the sensor takes the actual output and feeds it to the subtractor, okay, this error, this summing junction or whatever, that compares the demand, the set point value, with the output of the sensor to produce an error. Okay, so the error is the change between this and this will give us an error. Okay, and they're all connected by these arrows, which are used to represent signals. Okay, this is the basics of a block diagram, but like I said, we're going to look at them in a lot more detail in lecture 5, where we manipulate them, because block diagrams are often a lot more complicated than this. Okay. So you need to be able to manipulate them to get them into a state where we can analyse them. So control system design is all about understanding the general schemes that can be used to control the system. Okay. And to understand the system, okay, you need to predict how a system is going to behave. And that often involves mathematical techniques, okay? And it's generally all about differential equations. So if you're a bit rusty on differential equation manipulation and stuff, you might want to brush up a bit, because we do use them a lot in this course. Often, in the next lecture and the lecture after that, we implement a system that will make them a lot easier to manipulate. But for the first tutorial sheet, you need to understand sort of how to apply them to systems in real life. So the steps involved in control system design, okay, is you need to analyze the system. You need to work out how the system behaves and what you want the system to do, establish the requirements, okay? So if you're a control engineer being employed by a company to control a system, a customer, you need to go and talk to the customer to find out what the customer wants the system to do, okay? So establishing requirements. And from those requirements, you can then draw up formal specifications about what you need the system to do, okay? The system performance. And then what you can do is you can go back to your office after you've spoken to the customers and established the requirements. You can then sit down and try and model the system that we're trying to control, okay? And the system must accurately be modelled before controller design can commence, okay? And like I said, it's generally a system of differential equations. And obviously differential equations, we're talking about things that will change with respect to time, okay? That's what we're talking about with differential equations. d by dt, okay? This is fundamental. And then after we've done that, we can then develop a control algorithm, okay, or developing the controller. And the controller is developed using the model and the standard control theory to meet the specifications. I see some of you taking notes. That's fine. I'm pleased that you're doing so. These slides are also on Blackboard as well, so if you need to access them afterwards, then you obviously, of course, you can do that. The other thing that we're doing, I'm sure some of you have noticed, is that Simon at the back here has got a video camera and videoing the lectures, and these lectures are going to be posted online for you to access as well. Okay, so if you need to re-watch the lecture, then you're welcome to do so that as well. And again, you'll be able to access them via Blackboard. So these are the steps involved in control system design. And so, like I said, the first thing is modelling the system. We need to accurately model the system. Well, how do we go about that? Okay. Well, we need to understand the dynamic behaviour of the system. Okay. Obviously, if the system doesn't move or whatever, it's not really a system that we need to control. Okay. The piano's there. I don't need to control where the piano is. It's, that's not a dynamic system. But obviously, there are various dynamic systems, planes and cars and whatever, manufacturing processes, all these sort of things, and they're dynamic, okay, and we have to understand their behaviour. And so for the inverted pendulum, we need to understand the dynamics involved in an inverted pendulum, okay, the mathematics behind an inverted pendulum. And obviously, some systems operate in a linear fashion, some systems are non-linear. A pendulum that's, if we just think about a standard pendulum, okay, a pendulum that's just rocking backwards and forwards with small angles is very linear. But the moment you start rocking backwards and forwards at big angles, okay, that's highly non-linear, okay, which makes those triple pendulums, okay, an inverted triple pendulum, extremely impressive to watch because they're highly non-linear, okay, and highly chaotic. And they've managed to control them. They've managed to tame them using mathematics to understand what's going on. They've managed to tame these things that are highly chaotic and highly complex and non-linear. System dynamics is how its output changes in response to a particular input. So with any system, you have an input to it, okay? You need to understand how that input is transferred to an output from the system, okay? So that could be, like I said, aileron on an aircraft. Obviously, the pilot will control the aileron with a particular input. And that could be an electrical signal. That could be an actual force signal. They could be physically connected, okay? And the aileron will react, okay? It'll move up or down. Okay, and we need to establish the link between the input, okay, and the output of that system to be able to mathematically describe what's going on. And so as an example, think of a furnace, okay? You've got a room heater, okay? And you apply, let's assume this is like a gas furnace. Okay, there's a fuel flow into the furnace, and obviously the fuel is ignited. You get a temperature out the back of the furnace, okay? Now the thing is there isn't a direct link between the fuel flow and the temperature, okay? If you're pumping in, I don't know, 1 kilogram a second of fuel, okay, to get a temperature out the back, okay? If you suddenly change that fuel flow from 1 to 5 kilograms per second, you're not going to get an instantaneous response in terms of the temperature change, okay? It's going to rise gradually, okay? If perhaps from 1 to 5, it'll rise quite quickly. But, that's as an example. There's not a one-to-one relationship. The moment if you apply a step change in fuel flow, you're not going to get a step change in temperature. There's going to be a more gradual change in temperature. That's the same with your car, okay? Cruise control, you set it to 70. Say you want to break the speed limit and set it to 85, okay? You don't go suddenly from 70 to 85 in your car instantaneously. It rises gradually, doesn't it? And so, as we said, the temperature of the furnace does not change instantaneously for changes in fuel rate, okay? And so we use a differential equation to describe the influence of time on the response. Okay, that's the whole point of using these differential equations. d by dt, the change in some quantity with respect to time. And so we'll go through a few examples of that, okay? First off, let's look at the liquid level in a tank of fuel, or a tank of whatever. We'll look at an RC circuit as well, resistor, capacitor circuit, and then we'll look at a car suspension. I am aware that some of you are electricals, some of you are mechanicals, and we try to accommodate for both of you in these lectures, okay? So sometimes we'll be talking about electrical circuits, sometimes we'll be talking about mechanical systems like suspension systems, okay? But we do try and accommodate for both of those. Liquid level in a tank. Okay, we've got a tank here. Okay, there's a fuel flow in, which we call Q in. There's the height of the tank. It's got a constant cross-sectional area, A. Okay, and there's a fuel flow out. And we've made a statement that the outflow is just some constant multiplied by the height. So the higher the tank, the greater the fuel flow out is going to be. Okay, that's just that's the characteristic of this particular tank. Okay, cross-sectional area A, that's constant. And so we can make a statement saying something like the fuel flow in, okay, minus the flow out is going to be the rate of change of the height in the tank. Okay, now which makes sense. Yeah, if you turn off the tap at the bottom, if you just put flow in, so flow out is 0, flow in is the rate of change of. So you're putting in 10 litres per second into the tank. Obviously, the volume of the tank, or the volume of the water in the tank, is going to be increasing by 10 litres per second. Now, obviously, if you've got a flow out as well of 5 litres per second, then flow in minus flow out is going to be the rate of accumulation of water in the tank or whatever, okay, of liquid in the tank. And so there's a statement about how it performs, and then we can describe that mathematically, okay? We've got Q in and minus Q out is going to be the constant cross-sectional area, okay, well that's A. AH we know is the volume of the tank because we've got an area times by the height, that's going to give you the volume. A is a constant, so that can drop out, times by the change in height over the change in time. Okay, that makes sense, yeah? And we know that Q out is KH, so we can put that in here. And then we can put all the H terms on one side and the Q's on the other, and we end up with Q in is A dH over dt plus KH. That is a first order differential equation. Does everybody understand that? Yeah, we all understand what we got there? It's quite simple. That's a basic example. Okay, so we've got flow in minus flow out is the rate of accumulation in the tank. So there's our flow in minus our flow out, and then the volume, or the volume of the liquid in the tank is AH, and obviously the rate of change of that is d by dt of AH. Okay, now A is a constant, so we bring that out, and we just have with dH over dt, because H is not constant. H varies with respect to time. Okay? So there we have a simple example of getting a differential equation from a system. The next example was a resistor capacitor circuit. Okay, there's our circuit. Very simple. We have an input voltage. There's a resistor, and then a capacitor, and we can measure the voltage across the capacitor as our output voltage. Now we know we want to find the differential equation that relates the output to the input. And we know for a capacitor that the current going through a capacitor is the capacitance multiplied by the change in voltage over the change in time. Okay, that's the fundamental equation relating to capacitors. And then we can use the equation V equals IR, okay, voltage equals current multiplied by resistance, okay. Relating the input to the output, obviously there's going to be a drop across the resistor, and we know that drop across the resistor is due to the resistance and the current passing through the resistance. But we know the current passing through the resistance is going to be the current passing through the capacitor, and the current passing through the capacitor we know is the capacitance multiplied by the change in voltage over the change in time. And so for I in this equation, we can stick in this, okay, C dV out over dt times by R, and suddenly we end up with a differential equation relating V in and V out. V in equals V out plus CR dV out over dt, okay? Again, a first order differential equation describing this system. RC circuits are quite useful in various forms because they're like a very crude low pass filter. So say you've got something that's vibrating really, really quickly, okay, but you just want to measure the sort of average value, okay, you can stick an RC filter in and that will cut off those really high frequency things. And so these are used all the time in systems, okay? Even mechanical systems. So we're not, we are connected by the fundamental engineering behind it all. A car suspension system, well, we can model a car suspension system or one corner of a car using a very crude mass spring damper, okay? There's our mass. We've got a spring with a spring constant K, and then we've got a damper with a damping coefficient we call D. Okay, we apply a force, F, in to the mass, and the mass will move in the direction X. X, let's say, downwards is positive. Now we know the equations relating these things, but obviously Newton's second law, you should all be familiar with that at least, that force is mass times acceleration, and obviously acceleration is the second derivative of x with respect to time, okay? d2x over dt squared. Damping, well damping is generally, if you've not come across that before, damping is generally a damping coefficient d, okay, and that varies depending upon the velocity of whatever you're damping, okay? If something's stationary, there's no damping doesn't do anything, okay? And then the spring is obviously the spring constant multiplied by the change in displacement, okay? So there's three equations that relate to this, three forces in a sense that are input on this mass. The force is obviously the input force, okay? Be that the road or something else. And so we can apply Newton's second law. Newton's second law says the sum of all the forces equals mass times acceleration. Okay, so here's mass times acceleration equals the sum of all the forces. We've got minus kx minus d dx over dt, because both of these forces, the spring and a damper, will always oppose motion. Okay, if you have a spring and a damper, they always oppose motion, so that's why there's minus signs here and here. And the force is in the same direction as x, it's both downwards. Okay, so that's a positive. And if we stick all the x terms on one side, we end up with m d2x over dt squared plus d dx over dt plus kx equals input force, okay, F in. And there we have a second order differential equation, okay. So, these are basically describing the system, okay. We've got an equation down here, differential equation that will describe that system. Now there are ways that we can go about solving differential equations, but like I said, next week we're going to cover an easy way that we can manipulate these, okay, and put them into what we know as transfer functions, where we can analyse them in control systems. So that's more or less it for today. Let me just give a quick overview. So control is an intrinsic part of humans and a vital part of many engineering systems, okay? Think of any system and there'll be a control system behind it, I'm sure of it, okay? And the more, as things advance, more and more control systems evolve. Think of a car nowadays, okay? Cars 50 years ago didn't have a control system controlling the fueling and stuff. They used mechanical devices like carburetors. But nowadays, the fuel that's being input into the engine of your car is controlled using an electronic control system, okay? It measures things like the exhaust gas, all the chemicals and pollutants in there, and will alter the fueling depending on the control system, okay? As a simple example. Okay, so, but to be able to control the system, we need to know how the system behaves, how it works, and how controlling it will change it, okay? And so to do that, we need a description of the system, okay, and that will be the starting point of the control system design process, which you'll become experts at by the end of this course. And so the first thing, tutorial sheet 1, is on Blackboard already, okay, and it's all about determining the differential equations associated with systems. There's only 4 questions, okay, so it shouldn't, for those of you who have got their tutorial coming up, I know some of you have had a tutorial already, and I'm not quite sure what Sabir did during that tutorial, but he seemed to be pleased with it. But this is on Blackboard now, okay, and so we may, because there's only 4 questions, we may not need all 2 hours, but we'll find out, okay. So that's tutorial sheet 1. That's on Blackboard. If you could download it before and print it out before the tutorial session, then that would be good. And if I don't see you this evening, I'll see you next week. Thank you.